Hey everyone, today we're going to talk about one of the most basic, most important building blocks in all of programming, the array. Seriously, it's like the original super organized bookshelf for programmers. And to see why we even need it, let's kick things off with a really common problem.
So, picture this. You're building an app for a teacher, and you need to store 100 different test scores. Just pause for a second and think, how would you actually do that? What's the first approach that pops into your head?
You could just create 100 separate variables, right? You could have score 1, score 2, score 3, and just keep going all the way up to 100. But yeah, you can see the problem here. It is messy, it's a nightmare to manage, and it just doesn't scale at all. There has got to be a better way.
And that better way, of course, is the array. An array is basically just a collection of items, but with a few very important rules. They all have to be the same type, and they're all stored one after the other in a single unbroken chunk of memory. That bookshelf for mailbox analogy? It's perfect. Each item has its own numbered spot, so you know exactly where to look for it.
So here's what we're going to cover. We'll start with what an array really is. Then we'll jump into how to use them in Java. We'll look at the different kinds of arrays, the most common things you do with them, and then we'll get into the nitty-gritty of memory and performance. And finally, we'll wrap up with a recap.
All right, let's dive in and really break down this core concept. What makes an array an array?
Okay, there are 3 rules to live by when you're working with arrays. Number 1, they have a fixed size. When you create an array to hold, say, 100 scores, that's it. It holds exactly 100. It's not getting bigger or smaller. Number 2, they are homogeneous. This just means every single item inside has to be the same type. All integers or all strings. No mixing and matching. And finally, number 3, and this is their superpower, indexed access. Every slot has a number, and really importantly, that numbering starts from 0. This index is the key to their incredible speed because it lets you jump right to any element you want. And this really gets to the heart of what a data structure is. It's not just a bucket to throw data into. It's about how that data is related. An array creates a simple, clean, linear relationship. Each element follows the last one in a perfect, predictable line.
All right, enough theory. Let's see what this actually looks like when we start writing some Java code.
In Java, making an array is kind of a 2-step dance. First, you declare the variable. Think of int array scores as making a label that says an array of integers will go here. Then you actually create or instantiate the array with the new keyword. That's the part that tells the computer, okay, set aside enough memory for 10 integers. And Java's nice enough to fill all those new slots with a default value, which for integers is just 0.
Now, of course, you can do that all on one line, which is what you'll usually say. And even better, if you already know what you want to put in the array, you can use what's called an initializer list. Just use those curly braces. The compiler is smart enough to count the items and make the array the right size. Now, you might also see the square brackets after the variable name. That's a C-style thing. It works, but the modern Java way is to keep the brackets with the type. It just makes it clearer you're dealing with an array of int.
So, not all arrays are just a simple single list. They can actually get a lot more interesting.
The one-dimensional or 1D array is what we've been looking at. It's just a basic list. But you can also have 2-dimensional arrays, which are basically grids. Think of a chessboard or a spreadsheet with rows and columns. You can even have what are called jagged arrays. This is an array of arrays, where each row can actually be a different length. And don't forget, you're not limited to simple things like numbers. You can make an array of pretty much anything. An array of customer objects, an array of products, you name it.
And here's what that looks like in code. A 2D array gets 2 sets of brackets. So new int3 4 gives you a grid with 3 rows and 4 columns. For a jagged array, that initializer syntax is super helpful. You can see here we're creating 3 rows, and they have 1, 2, and then 3 elements each. It's pretty flexible.
Okay, we've created our arrays. So what are the common things we actually do with them? Let's talk operations.
This right here, this is the star of the show. If you know the index of the item you want, getting it or changing it is one of the fastest things a computer can do. We call this O1 or constant time. What that means is it takes the same tiny amount of time whether the array has 10 elements or 10 million. It's a direct jump, and we're going to see why in just a minute.
But what if you need to find something and you don't know the index? Well, the simplest way is a linear search. You just start at the beginning and check every single spot. This is what we call an O of n operation, because in the worst case, you have to look at all n elements. But there's a much faster way, binary search. The catch? The array absolutely must be sorted first. Binary search is wicked fast, O of log n. because with every guess, it cuts the number of things it has to look through in half. It's a classic trade-off. You do the work of sorting up front to get blazing fast searches later.
So this brings us to the array's biggest weakness, that fixed size. If you want to add or remove an element from the middle, well, you can't just do it. You have to perform a little bit of surgery. You have to create a brand new array of the right size, copy everything over from the old one, and along the way, you either add in your new element or skip over the one you're deleting. It's an ON operation because you have to touch every single element to rebuild it.
So why are arrays built this way? Why are they so rigid? The answer to all of this, the good and the bad, is all about how they're laid out in the computer's memory.
Here it is. The secret sauce is something called contiguous memory. It just means all the elements in an array live right next to each other, side by side, in one continuous block. This is what makes that O1 access possible. To find, say, the 50th element, the computer doesn't search. It just does one piece of simple math. It takes the memory address where the array starts and adds 50 times the size of one element. Boom, it has the exact address, instantly.
And this really highlights the big trade-off when you compare an array to something like a linked list. An array is one solid block. A linked list is a chain of separate nodes that could be scattered all over memory. That structure makes linked lists really flexible and fast for inserting and deleting things, but it makes finding an element slow because you have to follow the chain. So arrays give you that fast random access, but linked lists give you fast and easy resizing. It's all about picking the right tool for the job.
So let's just put that all in one place. This is a great little cheat sheet for array performance. Accessing or updating by index, O of 1, super fast. Searching, O of n, unless it's sorted, then it's a much better O of log n. And those expensive operations, inserting and deleting, are O of n, because you have to do that whole rebuild process.
Okay, let's wrap this up with a few key takeaways and best practices.
First, just remember that arrays are fundamental. They are a core tool in every programmer's toolbox. Second, their speed is in the index. You always want to use that direct access whenever you can. Third, watch out for the index out of bounds exception. We've all done it. You have an array with 10 items, which means the indices are 0 to 9. If you try to access index 10, your program will crash. And finally, choose wisely. Arrays are fantastic when you have a collection that isn't going to change size a lot. But if you know you're going to need to add and remove things constantly, something else might be a better fit.
And that really leads us to the final big question. Arrays are great, but what do you do when you don't know how many items you're going to have? What if you need something that can just grow and shrink whenever you need it to? Well, that's where things like the array list come into play, but that's a story for another time.